Hello folks, how's it going? This is Mike coming back at you here with another video on number theory. In the previous video, we saw some more sample problems about how we use the division algorithm to prove some facts about numbers. In this video, we're going to continue on in chapter 2. We're going to talk about the greatest common divisor of two numbers. Now, this is something that you should all have seen and learned about in math classes going back to prior to high school, intermediate school, middle school, just somewhere in there. From our previous video, or the one before that, we know that if we have two integers, a and b, and typically we assume that a is greater than b, by the division algorithm, we can write a as q times b plus r, where r is greater than or equal to 0 and strictly less than b. This is just restating the division algorithm. The most significant of all cases in the division algorithm is when our remainder is 0. That is to say, when we just have a equals q times b. So we can nicely, we can put a nice whole number of b's in to get a. When this is the case, we say that an integer b is divisible by the integer a, that's not 0. But more commonly, and you'll hear me use this phrase more often throughout this video and for the rest of the course, we say that a divides b. So b is divisible by a divides b, all saying the same thing. And we say these if there is some integer c such that b is equal to a times c. And this is the definition of what it means for a to divide b, or for b to be divisible by a. b is divisible by a, or a divides b, if there is some integer c such that b equals a times c. Of course, mathematicians have a symbol for this. Symbolically, we write a and then a big vertical bar and then b. If b is not divisible by a, then we put a slash through that big vertical bar and we write it as such. A, big vertical bar with a forward slash through it, and then b. And saying a divides b is right here, a, big vertical bar, b. Next up, we have some basic yet important properties about the divisibility of integers a, b, and c. First one, just a few really basic, really common sense ones. A divides 0. Any whole number divides 0. That makes sense. 1 divides any whole number a. And then any whole number a divides itself. Those are all pretty basic, all pretty straightforward. Number 2, a divides 1 if and only if a is plus or minus 1. That makes sense. There's only two factors of positive 1, and that's plus or minus 1. 3, if a divides b and c divides d, then ac divides bd. So the products of numbers, or of a number that divides some other number, those products also divide as well. Number 4 is the transitivity property. If a divides b and b divides c, then a divides c. Number 5, a divides b and b divides a, if and only if a is equal to plus or minus b. If you think about it, that just makes sense. Nothing too crazy, nothing too complicated happening there. Property number 6, if a divides b and b is not 0, then in absolute value, a has to be less than or equal to b. And that makes sense because saying A divides B means that we need to multiply A by something to get B. So A should be either the same as B or it's going to be smaller than it in absolute value. Number 7 is a very important property. We're going to see this guy coming up later on in this video, as well as in other portions of this chapter and in other portions of the course. If A divides B and A divides C, then for any integers x and y, any whole numbers x and y whatsoever, A divides bx plus cy. What property number 7 is really saying here is that if A divides B and A divides C, then A divides any linear combination of those two numbers B and C. So property number 7, as well as properties number 3 and 4, those are the 3 most common ones that we'll be using throughout this course. The other ones are just kind of basic things, not that they are explicitly used in the proofs of mathematical theorems or facts or anything like that. So we'll use these basic properties in conjunction with the following definition throughout this entire course to develop some key concepts. And this is the statement of the definition of the greatest common divisor of two integers a and b. So let a and b be our two integers, with at least one of them not being 0. Then the greatest common divisor of a and b, which we denote by GCD of a and b, GCD, open parenthesis, a comma b, close parenthesis. It's the positive integer, we stress the positive integer, d, such that d divides a and d divides b, and 2, if c divides a and c divides b, then c is less than or equal to d. Condition number 1 here, just saying d divides a and d divides b, shows that d, what we claim is the GCD, or the greatest common divisor, is indeed a common divisor of those two numbers a and b. So this just shows d is a common divisor. That's what number 1 is saying. Number 2 in this is what tells us that it is the greatest common divisor of the two. D is the greatest. So that's where those two pieces are coming in. One is just saying, okay, this thing is a common divisor. The second piece is saying, okay, it's the largest one. So with this definition and with the theorems that we had talked about before, let's get into some other interesting and useful theorems. First one up, very important. We are going to be seeing this result later on in this video and later on in this chapter and so on and so forth. Again, given two integers, a and b, not both of them being 0, there exist integers x and y such that ax plus by is equal to the GCD of a and b. What this is saying is that you have two integers, a and b. You can write the GCD of those two numbers as a linear combination of the two numbers themselves. Now, this theorem simply says that there exist these integers x and y such that you can do this. It doesn't tell you how to find them. How we find them will be coming up in the near future. There's a corollary that we get from this theorem here. If you take all linear combinations of A and B, so take A, multiply it by any whole number, take B, multiply that by any other whole number, could be the same, but it doesn't have to be. Add those things up. If you take all possible linear combinations of A and B and put those all inside of, and make those all elements of a set, what you have is the set of all multiples of your GCD. And that's really neat. Not something that we explicitly use a lot in math, but just a neat little fun thing to say that, oh, this is what we have here. The next theorems involve the assumption that the GCD of A and B is 1, which is important enough and occurs often enough to warrant a special definition. If two integers A and B have a GCD of 1, then the integers are said to be relatively prime. I'm sure you've heard of that phrase before as well. Just going to put it in the context of some number theory notation. Our first theorem that involves numbers being relatively prime. Suppose you have two integers, A and B, not both of them are 0. Then A and B are relatively prime if and only if there exist integers x and y such that 1 is equal to ax plus by. Now, this may seem very familiar. It may seem like we are repeating this result right here, which we just mentioned. And that result is involved, but it's not quite the same thing. If you reread this sentence carefully, this is an if and only if. So this is a biconditional. So if you know that A and B are relatively prime, then you know there are integers x and y such that 1 is equal to ax plus by. Also, if you know there exist integers x and y such that 1 is equal to ax plus by, then you know that A and B are relatively prime. The result up here is a conditional, not a biconditional. This guy here is only one way. We cannot assume the converse. So I have written out the proof of this theorem here. I've shown it both ways. One way is a lot easier, assuming that two numbers are relatively prime, and then showing that you have the integers x and y. That is just the straightforward use of the theorem that we stated at the top of our previous page. Going the other way is what involves a little bit more work. So I'll go through this portion of the proof in a little bit more detail. We're going to assume that there are integers x and y such that 1 is equal to ax plus by. And we're going to give the GCD of these two numbers some name. I'll call it lowercase d. What we want to show is that d has to be 1. So by definition of d being the GCD of A and B, d has to divide A, and d has to divide B. And going back to our basic properties of divisibility, you think back to property number 7, d then divides any linear combination of A and B. So therefore, d has to divide A times x plus b times y. Well, by our assumption, ax plus by is equal to 1. So d has to divide 1. Now this only leaves two options for d. D is either -1 or D is +1. I'll just make that note on the side here. So D is either -1 or D is +1. But D is a positive whole number. So that excludes the case that D is equal to -1, and that forces us to conclude that D has to be 1. So the GCD of A and B is 1, and thus the two numbers A and B are indeed relatively prime. Now, this is not necessarily a proof that I'll ask you to feedback to me. Maybe an extra credit question on a test, but nothing that you would have to know as a test question that you would have to answer. It's a fairly low-level proof using some of our nice basic properties, so nothing too crazy going on there. Another result that you may wish to use later on in this course, but you don't have to, if the GCD of A and B is D, then the GCD of A over D and B over D is going to be 1. Again, I've provided the proof of this fact here. Again, you can read it on your own. Not too bad to go through and to understand and follow through with the logic of it, but again, not as important of a result, so I'm not going to spend the time going through the proof in detail. Couple more here. If A divides C and B divides C and A and B are relatively prime, then the product AB will divide C. And then there's a lemma that's called Euclid's lemma. If A divides B times C and A and B are relatively prime, then A has to divide C. Just one last point here at the end. I will let you read that on your own. In essence, a restatement of what we had talked about earlier on in this video, with the exception of property B. Again, in integers A and B, not both of them 0. You have the GCD of A and B, call it D. The GCD is that thing if and only if D divides A and D divides B, as well as if C divides A and C divides B, then C divides D. Earlier, we said that C would have to be less than or equal to D, but now we're also adding that C divides D. So that's the one little thing that we're changing here, the one little extra piece of knowledge that we know. So that's it for this video on the GCD of two numbers. In the next video, we're going to see how we use some of these theorems and how we use the division algorithm to find the GCD of some larger numbers using a special algorithm called the Euclidean algorithm. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.